Hello my friends, today we discuss maximum power transfer theorem, which is a theorem that follows after you've done nodal Thevenin's and Norton's theorem, and it's highly related to Thevenin's and Norton's theorem because you have to use those theorems to come up with most of the solution, and then you just have to determine the maximum power that's coming from the source to the load. Now, maximum power transfer theorem states that the power transferred from the supply source to the load is at its maximum when the resistance of the load is equal to the internal resistance of the source. This implies that when you look at, we're saying the resistance of the load must be equal to the internal resistance of the source, or in other words, we are saying the load resistance must be equal to the Thevenin's resistance. So when the Thevenin's resistance is equal to the load resistance, then the power that we have is at its maximum. How we tell this? So when we look at the graph, when we're plotting variables or values of R Thevenin, the load resistance, when we reach a point when the resistance reaches R Thevenin, which is equal to the load resistance, then we find that we have the maximum power delivered to the maximum power delivered to the system. So in this case, you notice this is the peak point where we have the maximum power, and this is when the Thevenin's resistance is equal to the load resistance. This is the theorem of maximum power transfer, and this is what we want to calculate and analyze and look at. Now, if we come to calculating the current in the circuit, you realize that the current is then found from V Thevenin, which is the Thevenin's voltage, over the sum of the Thevenin's resistance plus the load resistance. And this is coming from, if you look at this circuit, what you only have in the circuit here is just the Thevenin's resistance and the load resistance. So the sum of these two comes up with the total resistance in the circuit, and this is the voltage across. And this is why this current, so if we come up with total resistance in here, for instance, if the total resistance comes up, which is the sum of R Thevenin plus RL, then the total current passing through in the circuit will simply be equal to V Thevenin over that total resistance, which is the sum of R Thevenin plus RL, as we are showing in the next slide. So that is how we find the current in the circuit. So to find the power, we get the power now, which is coming from I squared R. If this is I, then this is our I squared, and then multiplied by the load resistance, and this is our maximum power. How do we find the maximum or the maximum point? How do we come up with this? When we take the differential of the power on the load resistor over the differential of the load resistor, what we obtain when we expand, taking note that if we take du over v, which is u prime v minus u v prime over v squared, then what we lead to the maximum point to be equal to, generally you get to find R Thevenin to be equal to RL. When you do the manipulation of calculations here, you find that R Thevenin is going to be equal to RL, and that is from where we determine now the maximum power transfer. So from this point, the maximum power transfer is therefore equal to V Thevenin squared over 2RL squared multiplied by RL. So this is now the current I squared RL. And from there, if you expand below here, you have you have 4 RL squared, and here you have VThevenin squared. The RL cancel out and you remain with 4 RL watts. And this is how we get the maximum power transfer. Now, let's look at one example and maybe another example, and we see what happens. So here's a question. The question says, what is the maximum power that can be extracted from the terminal AB, which is these terminals AB? And you've been asked to find the maximum power. So you can use any preferred method. You can use nodal analysis, you can use mesh analysis, you can use any method that you prefer to find the solution. And in my solution, I come up with the VThevenin, which is the open circuit voltage, VOC. So you've got plus minus VOC, which in this case is the Thevenin's voltage. And what I come up with is my Thevenin's voltage is 5.5 volts is the VThevenin voltage. And you can verify that. So from the VThevenin and then the total resistance, if you calculate in the circuit, you will realize that the total resistance is basically 1. What you have, if we had to go back to analyzing how we get the total resistance, you see that when we zero the source, meaning the current source is zeroed by open circuiting, and then the voltage source is zeroed by short circuiting. So what you remain with is a resistor parallel to another resistor, which is a 2 ohm resistor, and you've got the terminals A and B, and then you've got both are 2, so it is 2 times 2 to find the total resistance there. You have 2 times 2 over 2 plus 2, which is basically 4/4, giving you 1 ohm, and that 1 ohm is the Thevenin's resistance. Having found the Thevenin resistance, then we now look at how to find the Thevenin's voltage, and thereafter we follow it up the calculations to find the maximum power. So we determine the current from this equation. I is equal to VThevenin over R Thevenin plus RL, which is 5.51 plus 1, basically 2, and it gives us 2.75 amps. Now to get our power, maximum power, we have I squared R, which is 2.75 squared times 1, which is giving us 7.5625 watts. This is the equivalent circuit that we have. Our equivalent circuit, the VThevenin, the R Thevenin was found to be 1 ohm. This is the load resistance. So we are saying for maximum power transfer to occur, the load resistance must be equal to the Thevenin's resistance. So once we find the Thevenin's resistance, then we know that it must be equal to the load resistance for us to find the maximum power transfer in the circuit. And basically that's how we do it. And then we'll look at example number 2. In example 2, we're looking at the question which says find the value of the load resistor RL that gives maximum power dissipated and determine the value of this power. For us to do so, we have to determine the value of the Thevenin's resistance, and that Thevenin's resistance value should be equal to the load resistance value for maximum power transfer to occur. So how do we do that? We have 3 scenarios that we can look at. So we could use mesh, we could use nodal, we could use maximum, we could use voltage divider rule. So let's look at these three methods and see how we solve the solution. These are the three methods that we could use. So one of them is mesh, and if we create a mesh circuit, so we have a mesh here. First, as you know, we take out the load resistor and we remain with an open circuit on this side where we have VOC, same as here, VOC. And so when we take the mesh and we take the current here to run anti-clockwise, and what we obtain to determine the value of the current I, because we are interested in determining the voltage across the 12 ohm resistor for parallel circuit, that voltage across the 12 ohm resistor must be equal to the voltage at the open circuit terminals. Therefore, if we determine that, what we have is I multiplies by 12 plus 3, which is this resistance there, and this must be equal to 15. And if we determine this is basically 15I is equal to 15, and I therefore is equal to 1 amp. And if we know that the value of the current I is equal to 1 amp, and there we can find the Thevenin's voltage, or the voltage across this resistor, by multiplying the current multiplied by the resistance. So we could say VOC equal to V across the voltage across the 12 ohm resistor, and that is equal to current, which is 1, multiplied by the resistance, which is 12, is equal to 12 volts. In other words, you could use this circuit branch, which has the battery or the source. So in this case, you could say E Thevenin will be equal to the source, which in this case is 15, and that subtracts the current through the voltage drop across the 3 ohm resistor, which is 1 times 3, which is 1 being the current I and 3 being the resistance, and this must be able to give you 12 volts. So that's the way we find, and this is the same as VOC or E Thevenin. So this is the same that you can find. And then in other words, you could also find the voltage VOC using the voltage divider. So you've got the voltage division here. This is simply the voltage being divided in between here is basically the total voltage, which in this case is coming from the source, which is 15. It splits across these resistances. We're interested in the voltage across the 12 ohm resistor. So it's 12 over 12 plus 3, and that multiplies by 15. And this should be able to give us, this is 15, 15 and 15 cancels out. It gives us 12 volts. That is method 2. Then method 3, you could use nodal analysis, where you could say, okay, this node is a reference node, so this is 0 volts, and then we have only one terminal A here, VA, which I've labeled as VA, meaning this whole terminal is one node. And then from this node, we've got a current entering and the current leaving into ground. So the sum of currents entering a node must be equal to the sum of currents leaving that same node. So in this case, the current leaving here, I'll take it as minus VA over 12, and that adds to 15 minus VA over 3. This must be able to give me 0. In a nutshell, we are saying the sum of currents entering, this current is equal to that current. If we take this over the equal sign, these two are equal and same polarities. If we simplify this further, what we come up with is minus 5 VA plus 60, and that should be able to give you 0. And from here, VA should be able to give you minus 60 over minus 5, and that gives us 12 volts. Now, since 12 volts is the solution, meaning we found the VOC is also equal to 12 volts. So these are the three methods that you could use to get to to get to the solution that we are looking for. Let's look at, after finding the Thevenin's voltage, then we can be able to determine the Thevenin's resistance. How do we find the Thevenin's resistance? We zero the sources. So what we remain with in here is we just remain with the 12 ohm resistor and the 3 ohm resistor, which are parallel to each other. From there, we've got 12 ohms and 3 ohms parallel to each other. So at the terminals here, the R Thevenin that is seen is basically equal to 12 by 3 over 12 plus 3. And this gives us 2.4 ohms as the Thevenin's resistance. So in short, when you write the final circuit, the final circuit appear as follows: the load resistor there, and then this is the Thevenin's resistance, which we have found to be 2.4 ohms, and then what we found here as the Thevenin's voltage, or you can call it E Thevenin, which is the same as VOC. This was 12 volts. Now from here, you're able to determine that the load resistor must be equal to, for maximum power transfer to occur, what you have is the load resistor must be equal to the Thevenin's resistance. Therefore, the load resistor here is equal to 2.4 ohms. And thereafter, now we're able to determine the current or the power in the circuit. And if we're to determine the current, then our current I is simply equal to E Thevenin or V Thevenin over R, the internal resistance, or R Thevenin plus RL. And this is simply 12 over 2.4 plus 2.4, and that gives us 2.5 amps as the current. And the power dissipated in the load is P is equal to I squared RL, and that gives us 2.5 squared multiplied by 2.4 ohms, and that gives us 15 watts. And that is, in a nutshell, how we solve the maximum power transfer. So P max is equal to 15 watts, and that's the solution that we're looking for. I would encourage you to solve many more such questions so that you get to practice and know how to calculate the maximum power transfer. And then the questions are straightforward. Once you understand the principle of Thevenin's theorem, Norton's theorem, maximum power transfer, mesh, nodal, those are key analysis methods that will assist you to find the open circuit voltage, and then you can now apply the formulas for power to find the maximum power transfer. Thank you for watching. Please subscribe to this channel and stay safe. Good day.